Hello, this is a talk I'm going to give at Image Space Simulation for Industry 2021 at the Institute of Physics in London. My talk is about optimization and simulation of X-ray images and how we apply this to register surface models on synchrotron macrotomography data. So I'm Frank Vidal from Bangor University, and this work's been done with my PhD student Ewan Mitchell and a colleague from INSA in Lyon, Jean-Michel Létang. Some acknowledgement first, so some of my collaborators, Jean-Yves and Xé from Lyon, Wolfgang from ESRF for providing the data, NVIDIA for providing the graphics card that was used to develop and validate the X-ray simulation library, supercomputing Wiz for all the times that I use on the supercomputer, and all the volunteers who responded to the user study. So the main motivation for this study is that some microtomography data have very strong artifacts, and that make it very difficult to extract information from the images. So we wanted to provide an alternative to manual measurement, where traditional image processing technique will fail. So this is the sample we use. This is a tungsten fiber in a matrix of titanium, aluminum, and vanadium. So the fiber itself is silicon carbide and the core tungsten. And this is a typical slice that we'll get. So the beam is almost monochromatic, and you see these streaks. There are fringes here. That's the phase artifacts. The streaks are actually beam hardening and impulse response of the detector. So that made it very hard to segment. Like, we can't use thresholding or region growing, and we see that doing the measurement by hand was quite difficult. And when we see the quantitative analysis of this, like in this column, this is values from the literature. Here, this is from the experiment. And you can see that the linear attenuation coefficient from the tungsten is underestimated by a factor of 2, whereas the silicon carbide is overestimated by a factor of 2. The matrix is about right. So we asked people to extract measurements from the images. We had 13 people who responded, and we asked them to find the size, position, orientation of the matrix, find the size of the fiber, find the size of the cores. And thanks to you if you're here and responded. And here are some answers. So what we can see for the matrix, it's, well, you can see the max here it's totally off the median, which will offset probably the average. The standard deviation is high, and you can see the range of answers is high for the width, for the height, for the rotation angle, and for the center of the fiber, the matrix. So what it shows is it's very hard to rely on manual measurements. Like, this is prone to errors, maybe there's some bias. The median is probably quite a good guess, but then is how many participants do you need to find a good median value? For the cores, see, it's the range here is 12 micron for something that is very small. This is a huge range. For the fiber, for the silicon carbide fiber, the range is also 12, but this is a much larger object, so 12 is probably not that significant. So we can see again here that it's very hard to rely on manual measurements, at least on this data. So as an alternative, we propose image registration framework, so that use X-ray simulation from CAD models. So we have a model to simulate CT acquisition, and we're going to tune this CAD model and some of the acquisition parameters, so that the simulated data will match the data from ESRF, and an optimization algorithm will tune the parameters. The requirements, well, we need to simulate the city acquisition in an objective function, which is going to be repeated many, many times. So we have a trade-off between speed and accuracy. No Monte Carlo simulation use a GPU from very simple models like surface models. Our implementation is 100% open source. So everything is open source, image processing, optimization, the X-ray simulation that I wrote is open source as well. And we wrote a prototype in Python. So okay, it might not be the fastest, but at least we have a proof of concept here. And here you can see the CAN model. So basically it's a parallelepiped that's hollowed so that we can have the cylinders made of the fibers that are hollowed so that you go to the cores inside. Then we need to simulate the city acquisition, so how many angles and the geometric properties from the city acquisition, the detector parameters, and so on. And how do we simulate the X-ray projection? Well, we rely on the Beer-Lambert law. We see that we improve that to have artifacts. But consider that we're dealing with city data, so we have the flat field correction that is applied, and we can also linearize the transmission data to provide sinograms. So the Beer-Lambert law, as I said, we improve it, so we have polychromatism, phase, impulse response of the detector, and we also added the Poisson noise. In total, we have 24 parameters that needs tuning by the optimization algorithm. It'd be a bit too much to do in one go. I guess I haven't tried. So what we did, however, is to break the large problem into smaller components. First we register the matrix, then we find the fibers, register the fibers, the size of the fibers, maybe move a bit the fibers, add the spectrum, add the phase, add the LSF, add the noise, and at the end we should have a good model. So one of the main components of the framework is the objective function. So there are three components. Which image do we simulate and compare? Do we pre-process them? And how do we actually compare them? So there are three images we could consider: the raw projection after flat field correction, the sinogram, or the city reconstruction. We discarded the last one because we did not want to have the reconstruction in the objective function, because that could slow everything. It's true it might provide better result, but we just discarded it. So we only consider the projection and the sinogram. For pre-processing, we could do nothing. We could do a min-max normalization, so the value will be then constant between 0 and 1. We discarded it because that might be prone to sensitive to noise. However, we consider the zero mean unit variance normalization because this is very popular in machine learning and computer vision. So the average pixel value will be 0 and the standard deviation will be 1 after that normalization. And we consider 4 different comparison methods: CMA-E, which is super fast but robust to outliers; IMSA, which is relatively fast, almost as fast, but give a higher weight to discrepancies than CMA-E; SSIM and ZNCC as well, because they're popular in computer vision and have different properties. In total, we had 14 different objective functions, different metrics, normalization, non-normalization, and depending on the data we use. For each objective function, we did 25 runs on a supercomputer just to have data. That's 350 registration, and that took 23 days. Could have been less because we could run 5 jobs at the same time. So we could divide that number by 5 if we were lucky, depending on how the supercomputer was busy. On average, a registration is an hour 35 minutes. And we took the IMSE on sinogram with normalization as our baseline because that provided the best results. I know we had some outliers. Actually know what they are. It's one of the first run of the optimizations that did not succeed, and now we know how to fix that fairly easily. So these outliers are not a problem. So, however, we looked at the 3 best strategies and repeated the experiment on my PC just to show that, well, the supercomputer is actually slower. We wanted to see if it was faster, but actually the supercomputer is slightly slower than my PC because I got a more recent graphics card. That's probably the reason. And then we had to choose a optimization algorithm. We didn't want to faff tweaking parameters and so on, so we took CMA-ES, which is a evolutionary algorithm, and it's designed for very hard nonlinear convex problems, non-convex problems. It's considered like state of the art. There is no parameter tuning. You could just use the default parameters, and the algorithm is supposed to find the parameters itself. The only parameters you actually need is an initial solution and standard deviation. So we went for it, and as I said, we did not try to make it run well. Like we just use default values. So to simulate the CT scan, we set the fibers geometry, then the core, then the matrix. We simulate the row projection for each angle. We can add phase, beam hardening, LSF, flat field correction, Poisson noise, and the normalization, like linearization. And then we can run our pipeline. So from now on, I'm only going to show results with the RMSE on sinogram with normalization. First, we register the matrix. No beam hardening, no, like very simple model here because that's fast and that just works, as you can see here. Then we find the fibers. Then we simulate the fibers with default parameters for the radii, and you can see this is rubbish. So then we register the radii. So we just optimize the radii of the fiber and the cores, and you can see this is quite nice. Now you can see it does not overlap with the phase. So a guess is that we are underestimated the radius of the fiber here. And you can see a boom in correlation here, 88%, which is good. We move the fibers, so it's a very quick registration here. That improved further, 91%. We optimize the radii. It's not changed much, like pretty much the same. Now we add the beam spectrum. So here it's really the height here that matters. And it's proving, I mean, you can see here we have mostly primary energy, not much first harmonics, a lot more second harmonics. It improved a bit further, the correlation. The correlation is between the CT reconstructions. We only use the CT reconstruction here to see how good the registration is. And then here you can see the phase start to appear. And you can see that matches quite well the profile of the reference. And another thing that's quite well as well, it's the actual peak here, it's roughly the same height. And you can see here a boom in NCC again. So the correlation is 93%. We add the LSF. And you can see now we retrieve that dip as well very nicely. And the correlation is 94% now. So you can see the LSF here. It's quite sharp, but there is a long tail. So we measured that at the ESRF, and now we just tweak the parameters. And you can see here's a simulated fiber in the center of the slice, and here's a reference, and you can see this spot here is here, and you can see this dark spot around here. This is here, you can see this is here. So it's quite a good match, and the phase is actually matching perfectly when we do a checkerboard. So we're quite happy with that. We could add poison noise, but we had poison, so the correlation drops. And now what is interesting is to compare the manual measurements versus the automatic ones. So here I remove the outliers. We do not want to have a bias. So we can see that actually the manual measurements without the outliers are in good agreement with the registration for both the width, height, and rotation of the matrix. For the fibers and cores, we look at the manual registration and manual measurement, registration without artifacts and with artifacts. And what is interesting is that the registration with the Birlo is actually not working, and when we add the phase and so on, it's a lot better. So this is actually our baseline. So without artifacts, this is not very good. The code works well. However, it seems that the volunteers underestimated the size of the fibers due to the phase artifacts. And we could actually compute the contribution of each artifact source, phase, LSF, beam hardening, and try to suppress that from the initial, like the reconstruction. And now you can see the corrected slice here. So in blue, that's what we should have in if it was perfect. And what is nice is like you don't have this dip anymore. It's flatter here. Same here, it's flatter. So it's actually retrieving the data. And when we look at actual numbers, you can see we are a lot closer than the experimental values here, from 193 to roughly 300 to, I was 140. So the error is a lot smaller, like 45 versus 150. So we have recovered the quantitative values. For the fibers, this is, but well, not as good, I guess. It's not too bad, I have to say. For the matrix, it was better once it was corrected. So we're quite happy with that. So in conclusion, it might seem to be easy to do the measurement by hand, but actually we can't rely on these measurements. We've seen that they were very large outliers. So this is definitely prone to errors. We saw that if you wanted to do it automatically as a registration problem, we need to improve the simulation with beam hardening, LSF, phase. And the choice of objective function is very important to achieve a good result. So now there are limitations. So our method is only suitable when you can generate surface models. And it might not be trivial for complex shapes. And you will need to model all the geometrical properties, like if it's tilting, warping, if there are pores, fiber toes, even if it's small, simple shapes. This is not straightforward to do. So we need to be able to model or sample. For future work, well, we could address some of the difficulty with a deformable model. And what we'd like to do, based on what I just last presented, is a model-based iterative reconstruction to improve the quality of data. So I try to remove the artifact and improve the linear attenuation values. And you know, if you have a CT scan with artifacts and hopefully simple shapes, we'll be happy to try our framework on your data. And thanks for your attention.